Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hi students, so this is another class, simple harmonic motion. After simple harmonic motion, which is about waves. Periodic motion, is a little related to these ideas. Right? See, simple harmonic motion is also related to conserving fields and Newton's laws, and so this is the next step in that flow, right? So we will discuss, from what is a wave on until we, provide, reach a understanding of, how to look at waves, etc. And there is a science associated with that. It's a very complicated science. let me tell you, you will be facing if waves, particularly if you choose to go into physics in some form. Wave theory is essential to a lot of subjects, including like if you go into communication theory, electrical engineering, etc. It will just keep coming at you like a wave. So much for that. So today, as you know, we have updated our applications. So if you go to play.google.com/store/apps, and or you go to the Play Store and then you type in Sushruta com.JnanaMarga.Sushruta, you will find our app, JnanaMarga's flagship app for students preparing for NEET. It is a very good app. It comes with now the most important update that we are doing now is the assessment modules. For those of you who missed it or who are in the process of studying for the NEET exam, we also have a mock test. So Jnana Test Prep is our mock test app. So if you go and download Jnana Test Prep, then you can also access our test application. And you can get right now a mock test, a NEET mock test. So it's still 8-9 days away, right? The NEET exam is 8-9 days away. So I want to wish all our students good luck, and take advantage of the Jnana Test Prep app and take a few mock tests. 3-4 mock tests will give you a very solid feeling of what the exam feels like, and importantly, time management. Time management is very critical also in the NEET exam. In 3 hours, when you have to go to 180 questions, you have to plan your time. You have to allocate sufficient time for biology, chemistry, and then physics. I prefer that students take it in that order. You finish biology first, then you get through significant amounts of chemistry. Don't get stuck anywhere. Leave aside at least 1 hour for the physics. Although physics has only 45 questions, you will need at least an hour there, maybe even a little more. I don't know. So, but that's how I would go about it. So, start with the biology, finish it, go to the chemistry, finish it, and then go to physics, and then have at least an hour. And keep good pace through it. Biology moves fast, but then again, you have to read every question very carefully and answer it. Okay, that's the advice to the NEET students. The JEE students, I know some of you have. Today I thought was the last day for the JEE students, September 3rd, 26th. So the new batch of students, and for those who are, this is the second attempt, maybe, and you will be taking 2 more attempts. Here's your chance. Okay, what happens. You may have done very well, or you may not have done as well as you wanted to do, right? So now download the Ramanujan app, prepare with Ramanujan. So you go to Play Store, type com.jnanamarga.ramanujan, download the app, learn from it, use the assessment modules, take advantage of all that's available to you, and then go about it. Okay. So let me continue with the class. So what is a wave? Okay, so today we will be looking at a single wave, and what is the what is the mathematics behind waves? Now you have electromagnetic waves. We will be dealing with electromagnetic waves in the context of EM theory. So it is coming. We still have to do electromagnetic induction and then certain amount of field theory before we go to EM electromagnetic waves. But it's not that far away. Okay, but so to prepare for that, we last time I did waves, and then I went little bit into light and little bit into electromagnetics. So this time, because we have two parallel tracks, it's we will be going there as well. Okay. Now you want to understand the relationship between speed, wavelength, and frequency. As many of you know, there are different types of waves. There is, and we will go over that. Transverse waves and longitudinal waves. Right now, when the particles, I'll come to that, vibrate in the direction of the transmission of the wave, or when the particles vibrate perpendicular to the flow of the wave, right? So those are the two types of waves. Now, when we discuss waves on a string, then we'll discuss sound waves, and eventually we will then later segue into like things like Doppler effect, where there's a frequency shift, right? And also we will look at sound waves in a pipe. They love to ask those sound waves in a pipe questions, and you should learn to solve those problems. They are freebies actually, if you know how to, because there's not that much material there. You must know what is an open pipe, a closed pipe, and learn all the formulas associated. Anyway, so pay careful attention. Now, what is a wave? The repeating and periodic disturbance that moves through a medium from one location to another carrying energy is referred to as a wave. So look at this one, okay? The progressing wave. I don't know, if you have a thread, right, tied to say a wall, and you do this, right, you will see the wave moving, right? Now the now when the disturbance like goes from one place to another, we are saying that it is a traversing wave, right? But if the wave, like you have a stringed instrument, then you do like I'm sure a lot of you have done that, like a veena or a sitar, or a sarod, right? Whatever the instrument, people will go and, or a guitar, right? Whatever the instrument, people go and time like that, right? So now you have a stretched string. You tap it in the middle, it then vibrates, right? So that is like a standing wave. Now if you do this to a thread, the wave moves forward, right? So that is a progressing wave or a traveling wave. See? Now waves, when we say waves need a medium, right? But there are some waves that travel across empty space. Okay, the most famous is of course light, right? Light travels through empty space, right? Light is what we can see, we call it light, right? But it is part of a whole class of waves called electromagnetic waves. Okay, there are cosmic waves, gamma rays, etc., which just travel in the infinitum that we call space, that separates us from the worlds out there. Okay, so and how do we communicate with those worlds out there, if ever we have to, is through waves. Okay, so that's why we learn a lot about waves. Everything we touch, we do, right? They carry energy, and so we understand these things in great, with great awe, and also with great accuracy. We have to get our marks, of course, but there's another more important idea, that they are so part of our lives. So now a mathematical description of a wave. say at t equals 0, we have a parabolic wave of the form y of x equals a square minus x square. Okay, so at t equals 0, you have y versus x, right? So that is a wave, right? Okay. Now, as t moves on, right, the wave moves, moves. Let's say, okay, let's say it is moving in the x-axis, right? So it is a function that over a period of time is traversing. Okay, so at t, any time t, like when the maximum of the wave is at a point x equals x naught, you can have a corresponding y, right? So now you notice that the whole function moves, right? Y is not a function of x alone. It is also a function of t. Okay, so notice that there is this dual dependence. Okay, so here y is a function of x comma t. It is a square minus x naught square, right? So as time goes by, right, now if the speed of the wave is constant, right, throughout the motion, and say it is equal to v, right, then you can say that x naught equals, then x naught equals vt, right, and therefore a squared minus x minus vt. Okay, so a square minus x minus vt will give you the moving value of the wave, right? As t increases, right, the function is a different one. Okay, it is a square minus, right? See, if you had, let me go back to function theory a brief. If you had a function y equals f of x, right? The function y equals f of x minus k in brackets, right? Y equals f of x minus k just moves the function to the right by k. Okay. Now y equals f of x, the whole thing, plus k will move the function up. Okay. So now in this case, y equals f of x plus k, f of x or x minus k, f of x minus k will move the function to the right. Okay, so that's what he is doing. Okay, but how much has the wave progressed? It has progressed by vt, right? The whole, there was a single parabola, right? Now that parabola has moved vt. So when it moves vt, the new wave is, which was like here, is now there. That's all he's saying. Okay, and this part of it, right? This part of it, what does this part of it say? Okay, this part of it says that it's only a portion of the parabola. Below that, it is doesn't exist. Okay, so it's only a portion of the parabola. Everywhere else, the curve doesn't exist. And he takes that parabola and then he moves that parabola little bit, and he says that is the depiction of a, that is the mathematical depiction of a wave. Okay, y of x comma t equals a square minus x minus vt the whole square. So I hope you got the basics here, relating the mathematics to the idea of how a wave, moving wave is depicted. Okay, so now so let's say the wave was going this way, then you will have it's of a square minus x minus vt the whole square. You will have a square minus x plus vt the whole square. Again, f of x plus k shifts the curve this way. Okay, so that's all it is, and by how much it shifts, that is based on how much the wave has traversed. Okay, v times t. How much has it traversed? V times t. You have shifted it by v times t, by this much. Okay, so that's the basic idea. So now if you're going this way, x minus vt, this way, x plus vt. Okay, So now from the one can deduce that any disturbance given by f of x at time 0 will be given as a function of time. When the wave is traveling along the positive x-axis, we say x minus vt. The wave is traveling along the negative axis, f of x plus vt. So this much is obvious, comes from function theory in mathematics. Okay? The conditions in which the above equations are valid are the disturbance travels undistorted. Okay, so now what does that mean, undistorted? It means that the amplitude of the wave, right, is not slowing, right? So when you see the waves in the beach, right, the first wave, right, and so people will always try to catch that first wave. When you, I don't know if you've seen surfers, surfers in the ocean, they will try to catch that first wave and then they will bounce, that wave will bounce and then they will move with it. Okay. So now, right, there is dispersion in the case of the water wave, as you would expect, right? But there are certain waves which never see, which travel undistorted. Okay. Now, the condition under which this equation, this is the perfect condition under which the wave is a perfect wave. There is no distortion in the amplitude. There is no and it's traveling at a fixed speed, right? Waves can also slow down, right? You can start moving very fast and then you can slow down. Okay. So let's discuss the other wave briefly, the wave that's happening between me and you, right? This is the wave where my throat vibrates, right? Where there is my vocal cords, they vibrate, right? And that produces a sound wave. And that sound wave travels and hits the mic of my laptop, right? So that is the other way, right? So now all of you know sound requires a medium to travel, right? And it travels across that medium, right? And you also know that, if I was, here, my voice doesn't go as far, right? Or if you were very far away, right, the amplitude will distort, it will decline, right? So it is the amplitude typically that declines. Okay, so remember that speed and amplitude are different. Okay, remember also that speed and wavelength are different. Okay, so so that is what they mean dispersionless. Okay, you can change the wavelength, you can change the amplitude, right? So there's a lot of things that can change with respect to these things. Okay, so we will discuss wavelength very soon. I maybe got a little ahead of myself, but I wanted to explain the word dispersion. Okay, dispersion is the change typically not just so much in amplitude, but also it's also a change in the frequency. Okay. Okay. Now, another way of looking at the wave travel is by considering a time interval between the waves maximum. So now let's say you have a point, right? So the wave, the time interval between the maximum and the minimum reaching a particular point, right? So that's another way of looking at the wave travel. So if you have a cut and the wave is moving like that, right? The wave is moving, right? So now if you have a cut, at this point, it will go up and down, okay? So between the waves maxima and minima from a point, so let the time taken be t, then t equals x over v prime. Therefore, we have f of x comma t equals f of x equals 0 comma t minus x over v. And the wave is traveling along the positive x-axis, and f of x comma t equals f of x equals 0 comma t plus x over v when the wave is traveling the negative x-axis. So you can write it in that form as well. You can, okay. So so the important equation is, of course, this one. One-dimensional differential wave equation is given by this d square x by dx, d square f by dx square equals 1 over v square d square f by dt square. Okay, so this is the very generalized wave equation. Okay, so one-dimensional differential wave equation is given by that, and please note this equation because you will see it many times as you go about learning about waves. Okay, now let us discuss these undispersed waves again. Okay, so this is the differential equation, and this differential equation produces these kinds of waves. Okay, now the most common way, of course, is the sine wave, right? So it's the sine wave; it keeps moving, right? There is a sine curve, and the sine curve keeps shifting. Okay, now the in such a wave, right? Typically the period of the wave, right? We say that the period right now. So now you have a wave, it's a single frequency wave, and that wave is moving, right? The period of the wave is 1 by its frequency. Okay. Now there is another the distance between the two maxima is called the wavelength. Okay. See, the wavelength is the distance between one peak and the next peak. Okay. Assuming it's a periodic wave, right? So now the distance between the peaks is the wavelength. Okay, and the time t is the time taken by the wave to move from one point to another. Okay, so now at this point, let us say we are now at a maximum. Okay, now after a certain period of time, we will see the maximum again at this point. Okay, because the wave is moving, you will see the maximum again at this point. The difference between those two points in terms of time is the period. Okay, and how many times per second that happens is the frequency. Okay, if many times you see the maximum coming, how many times at a particular point you see the maximum coming, that is the frequency. Okay, so the period is the time between the two peaks. Okay, and the wavelength is the distance between the two peaks. So now these are all related, right? So how much time does it take, right, to travel a wavelength, right? That determines the velocity of the wave. We discussed the velocity here, right? V here is the velocity. Okay, V is the velocity of the wave, the disturbance traveling with a constant speed V. Okay, so speed and velocity is the same because it's a we use it very interchangeably. Okay, so V is equal to f lambda, where f is the frequency. Remember, note this formula down because you'll be using it all your life if you end up in some kind of mathematical engineering or something like that. And you should always know this formula: V equals f lambda. Okay. Now, the sinusoidal wave, which is traveling, has this form. Okay, and this is the initial phase of the wave. Okay, so the initial phase is whether the wave starts at like 0 or whether it could start at a initial phase. So that is what that phi is. Okay, but the rest of it is exactly the same as before. And notice all the you notice that you can we are going to end up with introducing these terms. A sine 2 pi. Why does the 2 pi come? Okay, 2 pi f, right? 2 pi f is what? Omega, right? What is omega? Omega, you already know, right, is the angular frequency, right? So 2 pi f is 2 pi by t is what? 2 pi by t is omega. Okay, and T is 1 by F. So 2 pi F is also omega. A sine 2 pi Ft or A sine omega t. Okay, A sine omega t gives you the wave traveling, right? But then it is also, that is just the moving wave, right? We also brought in the x here, if you remember, f of x minus vt. So you also have the x and you have the time varying part of the wave. Okay, so sine 2 pi times x plus or minus ft, x by lambda plus or minus ft. Okay, so note that, note this equation, a sine 2 pi. Okay, so now what happens when you introduce omega into this equation, which we are going to do, right? So we have v equals f lambda, right? And you multiply and divide by 2 pi, right? Now when you multiply and divide by 2 pi, you have omega, which is called the angular frequency, 2 pi f, and then you have the other factor, which is 2 pi by lambda, which is called the wave number, k. Okay, so you have kx minus omega t, a sine kx minus omega t. K is called the wave number. So that is the most generalized form of this equation, right? So there are two aspects to it. One aspect, which is the time varying movement of the wave, and the other is the is this function which is wavelength dependent. Okay, so keep that in mind. Keep that in mind. There are two aspects to a wave, right? One is related to its wave number and the other is related to its angular frequency. Okay, you can have a wave which is not a sine wave. You can have a wave which is a triangular wave. Any number of different types of waves. Now let's do a simple problem. Displacement y of a wave traveling the x direction is given by y equals 10 to the power of minus 4 sine 600 minus 2 pi plus 2x plus pi by 3. Okay, so now speed of the wave motion, right? You must always reduce it to this form and then use this, reduce it to this form and then remember v is equal to omega over k. Okay, reduce it to this form and remember v equals omega over k. Okay, okay, reduce it to this form and remember v equals omega over k. Okay, so, so in this case, what is k? K is 2, negative 2, right? Or 2, right? Kx minus omega t, right? So k is 2. Okay, what is the amplitude? Amplitude is actually negative, right? Because kx minus omega t, right? So amplitude is actually minus 10 to the power of 4, right? So k is 2, right? Omega is 600. So what is v? V equals omega over k, right? V equals 600 by 2. Okay, so that's the important idea here. You have to reduce it to this form. K is called the wave number, omega is called the angular frequency, right? So 2 pi by lambda, right? If you wanted the wavelength, you get the K and you write 2 pi by lambda, okay? And most of the ideas will probably revolve, they will really test you on this. This equation is a solution to this differential equation. Okay, so keep that in mind. So now let me move forward. Okay, so transverse and longitudinal waves. Okay, now a transverse wave, right? The wave moves in a certain direction, right? But the oscillations are perpendicular. Okay, so this is what happens, like when you do that string. If you had a string, or like when you have a thread on a you know, the particles oscillate. Like if you had the veena, right? The veena is a transverse wave. You do tatan, right? The vibrations are like this, but the wave progresses this way, right? So the direction of propagation of the wave, actually the veena is a standing wave, But the string, right, when you do that on the string, right, the particles of the string, they don't move that way. The wave moves that way, but the particles on the string don't move that way, right? Now, when you speak, right, like sound, right, sound does that, okay? These waves have the oscillation in the parallel to the direction of propagation of the wave. You know, they are in the same direction of the propagation of the wave. So sound wave, it happens by compression and decompression in front of the air in front of in this way. So I'm speaking, it's the particles are vibrating like this. Okay. Water is different, right? Like the waves in the water are different. Anyway, so the movement is even the movement, like in the case of sound, is along the direction of the wave. We say it is a longitudinal wave. Sound is a longitudinal wave, right? Transverse wave is like the string where the wave moves, but the particles don't move with it. Okay, the up and down motion of the rope is perpendicular to the direction of the waves. Okay, so now this is a loudspeaker. It's not a torch. The loudspeaker is blaring. Then all these particles are moving here, moving here, moving here. Right? Loudspeaker is blaring, singing Hindi songs in and so the air is moving back and forth. Okay, and so the particles are moving this way, this way, this way, right? And the wave is also moving this way, and the the song is playing maybe from a ice cream wala who's trying to sell his ice creams, and it is heard by someone else far away, right? All right, let's move on here. So now, right, omega over k is v. Remember that, right? And kx minus omega t, right? Omega over v is v. Now, the speed of waves on a string. So if the wave is traveling with a speed v, right, and t is the tension and m is the mass per unit length, you know this formula. V is equal to square root of t by m, where m is the, or mu, where mu is the mass per unit length. Okay, V is equal to square root of t by mu. Okay, and this can be derived, using, but today I am not going to derive this. Okay, v equals square root of t by mu. Okay, this can be derived. Now, similarly, in the case of sound, we have what is called the bulk modulus and the density. Square root of the bulk modulus of the medium divided by the density will give you the V. T over mu, B over rho, square root in each case. Okay, so we've already discussed this, right? So now, a uniform string of mass 20 meters is suspended from a rigid support. A short wave pulse is introduced at the lowest end. It starts moving up the string. The time taken to reach the support is V equals square root of T over mu. Okay, and so in this case, the time taken to reach the support is, right? So now V is dx by dt, right? And T is g times x, square root of g times x, right? Because the tension is mass times g times, right? See, the string below has a weight, right? So now that's what he is using there. Okay, m times x times g over L is the tension, right? This is kept at a uniform tension T. So the tension is m times at a certain height, right? The tension is given by m times x times g over L. Okay, so it is proportional to the length, right? So x over L is the portion of the tension that is being supported at a particular height x. Okay, so m times x times g over L. L is the total length, right? So now m is what? M is the same as mu. Here this is mu. Okay, so now the mu cancels, so you end up with xg over L. Okay, and that's how he then has this equation dx by dt equals square root of gx, and then he integrates the square root of gx over L, then he integrates that both sides, and then he ends up with t equals 2 times square root of L over g. Okay, and so from that, so he then plugs that in back in there, right? L is 20, g is 10, so square root of 2, so 2 root 2. Okay, that is derived by using this equation. Okay, so t equals g by x to the power of minus half dx equals g to the power of half dt. G is a constant, so dt becomes t, and x to the power of minus half becomes x to the power of plus half by plus half. So he does the integration from this step, right? That's how he ends up with 2 root 2. V is equal to t by mu, square root of t by mu. Now, and the other one is b by rho. Now, let's discuss periodic motion. Okay. Periodic motion deals, and then we will relate it to the idea of uniform circular motion, which is the case of a particle moving in a constant circle with constant speed. Okay. So, the relationship between periodic motion, motion in a circle, and simple harmonic motion, there is a important connection between all these three. In fact, they all deal with pretty much the same equation. Okay? And we will discuss the representation of several types of periodic motion in the displacement versus time graph. Okay? So now, periodic motion is a type of motion that repeats itself in equal intervals of time. A simple example is the case would be a particle going in a circle, okay, with a constant speed. X equals r cos theta, right? Now, but theta is changing, right? So if you have a particle moving in a circle, what is the position vector, right? The x component of the position vector is r cos theta, right? Theta is what is theta? Theta is based on the let's say it has an angular velocity, right? So if it's moving in a circle, has an angular velocity with a period t. 2 pi by t equals omega, right? So the x component is r cos theta, right? Or which is same as omega t, r cos omega t, right? So and that's how we look at these questions. Okay? That's how we look at the relationship between circular motion and periodic motion. Notice that the x component is a sine wave, as is the y component, or x component is a cos wave, y component is a sine wave, right? So the y component is a sine wave, x component is a cos wave. So in many ways, periodic motion is when componentized, uniform circular motion when componentized is actually periodic motion. So y of t is actually the x component or y component of t versus time. Okay, this is a very tricky and complicated idea. Okay, but it's an important and very fundamental idea that we all deal with. So now the Earth's rotation on its own axis, right? When the Earth rotates, right, the Earth revolves around the sun, right, 365 days, right? Now, what it also does is it rotates each day, right? It rotates, and that's why you have day and night, right? Now, how long does it take to do one full rotation? 24 hours, right? The moon goes around the Earth in 29 days. Okay, nobody cares about it rotating on about itself. So there's no people living there, So now the Earth goes around the sun in 365 days or 365 and a quarter days, right? Now, what is the frequency, right? So now the frequency is 1 over time. Okay, and so what is the angular frequency? 2 pi by t. Okay, and so the angular frequency, frequency equals 1 over period. T is the period, right? And so periodic motion can then be understood in the context of these very same laws. Okay, so now v, so if it's going in a circle, right, what is the velocity? The velocity is uniform circular motion, very simple, right? What is the circumference? 2 pi r, right? 2 pi r in one period, right? 2 pi r by t is the velocity, right? Or the speed. 2 pi r by v is 2 pi r by t is the speed, right? So now t is 1 over f, right? So f equals v over 2 pi r, and v equals r omega, right? V equals r omega, so f equals omega by 2 pi f, or omega equals 2 pi f. Okay, so these formulas you should know. We also introduced that k, which is related to wavelength, that is a little bit different. That comes only in the context of waves. Okay, now here there is no wave. Okay, so now we are going to manufacture it, by linking it to the wave. So you're plotting x comma y, right? So the x component and the y component, each versus time, is a wave, is a sine, is a sinusoid. Okay, so if you plot it over time, it will be a sine wave. Okay, so what is the x component about that circle? Is a sine wave. Okay, it's a periodic motion. Okay, so now any sine waves, right? Sinusoidal wave is basically it is a kind of simple harmonic motion. Simple harmonic motion also follows a sinusoidal wave, as you know, because we just dealt with simple harmonic motion, right? So this periodic wave is also in some way a simple harmonic motion. Now, there are different types of periodic motion. One of the students had asked me about this in recently. Okay, how is simple harmonic motion different from periodic motion? Okay, the main difference is in periodic motion you can also have a triangle. That is also a period. Anything with a period, it can have any kind of function. It can even be a step function. That is also a periodic function. Okay, in a computer, the clock follows a step function. Okay, that is a periodic. The clock of a computer versus time is periodic, and it happens on the dot at every dot. Okay, and so it follows that kind of what is called a step function. Okay, now this is a triangular function. Okay, now when we understand periodic motion, there are many ways of looking at these things, and you will learn a lot more about this as you go forward, right? You drop a ball, and let's say it bounces without losing energy, keeps going up and down. What is its y versus t? Y versus t will look like that. Okay, y versus t will look like parabolas, right? Y equals h minus half gt square. That is a parabola. Okay, so this is a parabola. Okay, so y equals h minus half gt square. So the y versus t graph is a parabola. Okay, and so now the different types of periodic motion, as I said, there's a triangular type of periodic motion, then there is the step type of periodic motion, +1, -1, etc. Okay, now and you can typically convert sometimes these kinds of waveforms when in certain cases when you need it. Okay, now a ball dropped will follow this kind of a periodic motion, right? Parabolas, right? And you can have other types of periodic motion, but the v versus corresponding v versus t will be a straight line, straight line, straight line. Why does it have this discontinuity in the straight line? Because it bounces back, right? It goes and hits, and after the collision, it is moving this way with the same velocity. Okay, that's what happens when you bounce back, right? You go hit it with a V, you rebound with a V. So that is what is happening here. So the V versus T, go hit, you're now travel at one point you're traveling downward with the velocity V. After the collision with the ground, it is traveling upward with a velocity, same velocity V, if it is a perfect collision without loss of losing energy, right? But as you know, it will bounce and decline, right? So this is in the perfect case, it is periodic motion. So simple harmonic motion is the case when you have y equals kx, so f equals kx, negative kx, right? Therefore, a equals minus omega square x, right? When a equals minus omega square x, you end up with the motion that is produced. The x of t versus the x versus t graph looks like a sine wave. Although the body is moving this way, this way, this way, this way, the x versus t graph looks like a sine wave, right? So that is the other case how these uniform circular motion and simple harmonic motion, all these ideas are related. So I'm going to stop here today, and we will continue our discussion next class. I will start right after simple harmonic motion. I will be starting the discussion with superposition of waves, and then look at we will look at standing waves, and then we will look at waves in the context of a pipe, etc. And then we will do some more problems. Okay, so wave theory is a very integral aspect of many sciences. So you should learn a little bit about that so that you understand how to use problems involving waves. There will be a portion of your exam which definitely deals with waves, particularly for physics students. It's very much a requirement. So I hope you've paid careful attention. Do some problems. Download our app. Do some problems. Very important to have students do that. So with that, I'm going to close today, and we'll meet again next class. And if it is Sunday morning, it's class 11. Sunday evening, it's class 12. We will be discussing continued material, and we will be going forward, there as well. Post magnetostatics, we'll be going to, AC circuits. We'll be doing induction, electromagnetic induction, etc. That will be going. That will also hit waves very soon. Okay, so look forward to seeing you all there as we progress forward. Thank you.